Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning about how to calculate theoretical n% yield. Now, when is this really important? Well, typically it has to do with stoichiometry and relating to your work that you do within the laboratory setting. Percent yield is equal to the actual yield, which is how much you obtain within an experiment, so it's also commonly called the experimental yield divided by the theoretical yield, which is how much you obtain when you calculate it using stoichiometry. So, just using your calculators and going through all the mathematical steps of what you've been learning about in general chemistry. And we times it by 100%. Now, why is it that we try to calculate this? Let's take a look at it. Now, throughout stoichiometry, we make the assumption that all reactants 100% convert to products, meaning that we are assuming that we are perfect. The thing is, as we all know, we are not perfect. We make errors in the lab. It is not possible to get 100% in chemistry. You always are making errors all over the place, which is normal. You make errors because you're learning, you're trying to get your lab skills better. Sometimes reactions don't completely occur the way you want them to, but there are errors, and these are things that we have to deal with. Now, where can these errors come up from? Well, sometimes they can come from maybe just transferring chemicals between glassware. It's really easy to see, like, hey, some solid got left here. Maybe when you're mixing, you see it on the stirring rod or on the spatulas or on the beakers. It's very common the reaction doesn't go to completion, where maybe you didn't wait long enough. Like, okay, the lab manual said 15 minutes, but hey, your lab partner wanted to leave a little early, so you just did it for 5 minutes. So maybe there was an error. Other things that could be made is maybe you made a side product, meaning that another reaction occurred without your knowledge, or the reactant isn't, or let's say the reactants weren't even pure to begin with. So let's say if you just had like some maybe not the best quality ingredients, well then yeah, you're gonna have different products in the very end, or just human error to begin with. Maybe you just made a mistake or forgot to do something or added too much water or whatever it is, there are going to be errors. So when we are calculating this, we calculate on paper the theoretical yield, which is something that you've been doing all along. This is all stoichiometry calculations. So whether it's mass to mass, gas stoichiometry, solution stoichiometry, you're assuming that you have a perfect experiment, right? This is all about mass conservation and being perfect. And that is a true law. However, we do make errors and there is mass that can be lost. So if something is lost, this is what the actual yield is and what we measure in lab. So we compare the two numbers to see, well, how good did you do when you were in the lab? It gives us a reference point to see, can we improve, right? One of the things about school is all about improvement and getting better, right? If you were getting 100% on everything going throughout the gate, then you don't need to be in school, right? You can just start working in the field that you want to be in. But we do this because we want to learn, we want to grow. And the whole idea here is when it comes to chemistry is products are always lost. We're always trying to search for them with our little magnifying glass, but we always are losing a little bit. So we're going to be using this formula to help us try to understand this. So let's try to take a look at an example of how this could work, and then we'll get into some harder stoichiometry examples. In the reaction box, there are 6 moles of hydrogen gas and 3 moles of nitrogen gas. Based on the reaction, determine the theoretical yield based on the following chemical expression. Well, if we were doing this and we wanted to figure out exactly how much ammonia you were going to make, which is your theoretical yield, what would we do? Well, the first thing is that we saw is that we had 6 moles of H2. So if we wanted to convert that using this formula, well, we would just use our molar coefficients, and we can see that, okay, for every 3 moles of H2, we are going to be making 2 moles of ammonia. So if we were to do this little conversion here, we're going to quickly see that we would obtain 4 moles of ammonia that are possible. Now, the thing is that this is a limiting reagent problem because you were given 2 different starting points. We were also told, hey, we have 3 moles of nitrogen in that box too, and we can see it as well. There are these little blue orbs that are here are reacting as well. So if I have 3 moles of nitrogen, and from our chemical equation, we can see that 1 mole of nitrogen reacts and it creates 2 moles of ammonia. Well, this is going to make a total of 6 moles of ammonia. Well, which one is the theoretical yield? Well, it's all about which made less out of the two. So our answer in this case is going to be that hydrogen was the limiting reagent, and our possible theoretical yield is going to be hydrogen in this case making only 4 moles of ammonia. Okay, so our theoretical yield is 4. Now, if we wanted to calculate, let's say, percent yield, how exactly would you do this? Well, so let's say if, however, you actually only created 3 moles of ammonia in the lab, what is your percent yield? Well, so this is your actual, which is 3. Your theoretical was 4. So what do you got to do is you'll take 3 moles, which is your actual yield, divide that by 4 moles, which was our theoretical. We calculated that together. So telling us that you have about a 75% yield within your reaction, which is pretty good actually in chemistry to get about a 75% yield. A lot of times when you're doing organic chemistry, you might be lucky if you even get 5 or 10% yield, depending on what reaction you were trying to do. So that's the basic idea. How much were you supposed to make and how much did you actually make when you did the experiment? All right, let's take a look at some different stoichiometry examples. From the air to form lithium bicarbonate. So lithium hydroxide plus CO2 makes lithium bicarbonate or lithium hydrogen carbonate. What is the percent yield of lithium bicarbonate for the reaction if 50 grams of lithium hydroxide gives 72.8 grams of lithium bicarbonate? So the first thing is that what a lot of students will do is they want to just divide these two numbers and then times it by 100% and think they are done. The thing is that would be very, very wrong. We can't just take 50 grams and divide it by 72.8 and be done with the problem. We need to convert it to be the same molecule when we are comparing the two numbers. So we need to do the stoichiometry for 50 grams of lithium hydroxide and then convert it to lithium bicarbonate. So in this case, using mass stoichiometry to do the conversion. So now whenever we do these, we always need to check if the chemical equation is balanced. Typically, the easiest way to know if it is if you see coefficients. But with this one, there are no coefficients, but you might be able to quickly identify that it is balanced. You have 1 lithium on each side, 1 carbon, and then 3 oxygens. So it's pretty quick to see that this one is balanced, so we don't have to do anything else. So what we are going to do is we need to calculate what the theoretical yield is using stoichiometry conversions. So we want to write down all the important pieces of information that we were given, which was 50 grams of lithium hydroxide, and then what our actual yield was, which was 72.8. Keep in mind, whenever there's actual yields involved, it's always generally given to you in some form, or it's what you did in the lab. It has to either be given to you or you did it yourself. There's no, you generally can't calculate it unless you were given the percent yield. You have to, usually something has to be given to you. So if we were to do this, we have 50 grams of lithium hydroxide, so LiOH, at our disposal. And we are going to convert this to lithium bicarbonate. So what is our first step to do that? Well, whenever we are given a mass, our goal is always the mole. So we need to use the molar mass of lithium hydroxide to get there. So what we'll do is we'll use our periodic table and you'll get 23.938 grams of lithium hydroxide. And if you're watching this, I recommend you check that so you can practice it. And that's equivalent to 1 mole of lithium hydroxide. Now from there, what we're going to do is use our chemical equation, which we can see it's a 1-to-1 ratio. So 1 mole of LiOH is equivalent to 1 mole of LiHCO3. All right, so that's a 1-to-1 ratio. And let's change the color of lithium hydroxide to match the formula too. Now from there, we're now going to use the molar mass of lithium hydroxide to cancel out the last part. But before we do that, let's just show our units are all canceling. So grams canceled grams. and then moles canceled moles. All right, so our molar mass of lithium hydroxide is going to be 1 mole is equivalent to 67.956 grams. And we can see that, hey, these canceled as well. So 1 mole cancels 1 mole. And what we will get in the end is 141.94 grams of LiHCO3. So this is your theoretical yield that we are here and we have labeled in pink. So what do we got to do now? How do we figure out the percent yield? Well, the whole entire thing with the percent yields, we got to kind of plug it into the formula below. So we were given 72.8 grams is how much we started with. So what we are going to do is essentially take that value and then divide it by our 141.94 grams. And we're going to times that by 100%. And what we are going to end up having in the end is about 51.3% is our yield in this problem. So, which is pretty good. I know it sounds like a really low number, but in terms of percent yields, this is pretty good for most chemical reactions. You always want to get higher, but it's not bad for a chemical reaction. Let's look at another example. So we want to find the actual yield in this problem. So we're going to be working backwards, meaning that aluminum reacts with oxygen to produce aluminum oxide via the following reaction. So we have 4 aluminum reacting with 3 oxygen to make 2 aluminum oxide. So what we are going to do is we're going to calculate the mass of aluminum oxide that can be produced if the reaction of 50 grams of aluminum with excess oxygen has a yield of 75%. So first things first is we need to calculate the theoretical yield starting with the 50 grams of aluminum. So we're going to convert that to aluminum oxide in this problem. So we got to kind of look through what all the important piece of information is. So right, there's a lot of words here, but we only need a few of these more important terms, which was essentially we have 50 grams of aluminum. Excess oxygen means it's not going to run out. And then we have 75% is what our yield is. So we're starting with 50. So what we're going to do is calculate what that theoretical yield is. So we're going to start with 50 grams of aluminum, and we need to get that to moles. So how do we get a mass to moles? Well, we need to use the molar mass to do that. So we're going to use our periodic table to see that, okay, 26.98 grams of aluminum is equivalent to 1 mole of aluminum. Now, we are interested in getting to the final product, which is aluminum oxide. So we need to use our molar coefficients to get there. So we see that 4 moles of aluminum is equivalent to 2 moles of Al2O3. Then we're going to use the molar mass of aluminum oxide to get 2 grams as our final step. So 1 mole of Al2O3 is equivalent to 101.957 grams Al2O3. Now, before we continue, we want to double check, did all of our units cancel properly? So we see grams are opposite each other. They canceled. Moles canceled moles of aluminum. And then moles of aluminum oxide canceled moles of aluminum oxide, leaving us only with the grams. So when we solve this, we'll take 50, divide it by 26.98, times by 2, divide by 4, then multiply by 101.97. And what we will get for a theoretical yield is about 94.5 grams of Al2O3. So this is our theoretical yield here, which is what we've been doing all along when it comes to stoichiometry. It's nothing new. It's just we're just labeling it a little differently. So calculate the actual yield. How do we do it? Well, the thing is, we were given that we had 75% yield in the problem. So what we are going to do is we're going to pretty much take the problem and plug in the theoretical yield that we got. So we have our actual yield, and then our theoretical was 94.5 grams of Al2O3. So the first thing we're going to do is we're going to move the 100% to the other side. And what we'll quickly get is, all right, 75 divided by 100, we'll get 0.75. And that's going to be equal to our actual divided by our theoretical. And then we will multiply both sides by 94.5. So that way we get that number by itself. They cancel out. And then what we will have for our actual yield is 70.9 grams. Is how much they actually got in lab. So this is if you had to calculate actual yield, but as I mentioned before, this has to be a number that's somehow given to you. As you saw, it was given via the percent yield this time. It's something that you have to physically do. All right. So this has been my video on percent yield and actual yield. This is just another check for yourself to see how you did when you're comparing your lab data to what you actually could theoretically get if the reaction went flawlessly. All right. So thank you so much for listening. If you need help, please reach out, email me, comment below, ask me in class. I hope that this does help you. If not, then I'm sorry. But if this is your first time here, please hit that like and subscribe button. Please keep supporting the channel. I really appreciate all of you, and I hope you have a wonderful day. All right. I will see you all later. Bye now.